Welcome back. We're going to continue our discussion on colligative properties. The second colligative property that we'll be looking at is elevation of boiling point. But first, let's understand what is boiling point. Here's a picture for you. Say you take a vessel, put some water in it, and put it on the stove and allow it to heat. Before you eat or while you're heating, you have molecules. I guess let's start from the beginning. When it's just water in the vessel and it's just put on the stove, you just have water in the liquid phase. But as you continue to put more and more heat into that vessel, molecules that are in the liquid phase go into the vapor phase, as it's shown here. You see, they're going slowly into the vapor phase, and there's more here. When they get into the vapor phase, they continue to collide with themselves and with the walls, generating a pressure, which we've already established as vapor pressure. So this is vapor pressure. And this is atmospheric pressure, which is the pressure of the room. When these two pressures equal, that's when a liquid boils. And this is the rule for any liquid, not just for water. So when vapor pressure equals atmospheric pressure, that's when any liquid begins to boil. How soon something boils, how late something boils, depend entirely on how fast this vapor pressure could be achieved that equates to the atmospheric pressure. But as I pointed out earlier, substances with higher vapor pressure, that's increasing vapor pressure, have lower boiling point. And substances with decreasing vapor pressure will have higher boiling point. That is, a deodorant, spray from a deodorant has a high vapor pressure, which is why it evaporates so quickly. In other words, it has a very, very low boiling point. Whereas substances like water has very low vapor pressure and in turn takes longer to boil. Okay, there are substances with even higher vapor pressure that takes even longer to boil. So, and also there's a general term that pure solvent will always have a lower boiling point compared to a solution because the solute lowers vapor pressure. We've already established that. Okay. So lower vapor pressures means it tends to have low vapor pressure, means higher boiling point. Okay. Along this line, I want you to learn something, which is, I'm going to actually delete this and then get back into full screen mode again. So I want less distractions on screen. This is called a heating curve, and this is for water. And this really brings out the idea of boiling. And I want to leave you with a practical application question. Why is it not advisable to eat snow if you're stranded in a blizzard while snowboarding on a mountaintop? Think about it. Hopefully this heating curve example or explanation would help you answer that question. Maybe not, I don't know. So you have several points on this graph. So say you start with ice, a block of ice, which is where you're at, and you continue to put heat, or just keep ice in your palm or on a table or in a glass, wherever it be, and it continues to absorb heat. So between A and B, the substance continue to be in the ice phase, but you see it's continuing to absorb heat. Between points B and C, now water is very unique. Water freezes and melts at 0 degrees. No other substance in the world can do that. So at B, towards B to C, it begins to melt. There's an equilibrium, it's a competition. And between C and B, backwards, it freezes. But say, that's why the temperature is flat, means it's not absorbing any heat, but it's using the heat to convert B to a C. At C, it's just water. Okay. At B, it's purely ice. Between B and C, it's a slurry. And then again, it continues to absorb heat. It still remains water at this point. Okay. Now, this is where this is just water. And again, here you have both water and steam. There's a competition. That is, forward, it's evaporation. Okay. And reverse is condensation. That's going from vapor to liquid. At E, you just have just steam. Okay. And anything past E to F is purely steam. Okay. This is really, really important. Okay. And whenever a line is flat, that means heat is the temperature. There's no change in temperature at that point. Means it's continuing to absorb heat, but there's no significant change in the temperature. Okay. This is called the heating curve. And I do want to bring this next screen up. So say when you put a solute into a solvent and bringing it to boil, the nature of the solute itself plays a key role on how fast or how slow the liquid boils. So this is an equation for elevation of boiling point. Again, you do not have to memorize this. And then the delta TB is the change in the boiling point, KB is the boiling point constant, M is molality, and I is Van Hoff factor. The only thing I really want to focus on this particular video as introductory is just the I. I is substance dependent. For instance, you have KCl, which is a metal containing compound, and say you have K2SO4, which is also a metal containing compound, and say you have methane, which is a non-metal containing compound. Here it's a metal containing compound. You have one of K, one of Cl, so I is 2. It's 1 plus 1. Here you have 2 Ks and 1 SO4. It's a metal containing compound, so I is 3. Here it's methane. It's a non-metal containing compound, so I is always going to be 1. So it's a non-metal containing compound. And that's very, very important. Okay. If you increase I value, boiling point increases. That is, more the I, it takes a lot longer to boil. We will do a math problem to really understand this, but this is what I want to drive it. So if your compound contains a metal, then you have to count the species. If your compound doesn't contain any metal, then I is just 1 for the entire compound. If I increases, boiling point increases. Okay, and this is where I want to stop this because I don't want the video to get too long. All right, stay tuned.